Perfect. So thanks everyone for coming here now this Chilean afternoon for the second talk. It is my pleasure to introduce the next speaker, Samuel Grushevsky from the wonderful University of Stony Brook. And he will talk about an explicit weak solution of the Schottky problem. Thank you, Samuel, for being here.
So thank you to all of you very much for inviting me. I'm glad to be here. I would have been even happier to do this in person, but maybe one day. So I wanted to talk about the Schottky problem and the work we have recently done with Herschel Farkas and Riccardo Salvati-Mani, who just came here. But instead of just talking about our work, I would like to give a panorama of the Schottky problem, and maybe you'll see some photos of other mathematicians. So here are Herschel and Riccardo. Herschel is somewhat less young now. I couldn't find any freely available photographs of Herschel online, more than once. I have my own, but he didn't authorize me to use them. So, well, these are Herschel Farkas and Riccardo, who is here. And this is the work we've done with them recently. And this is about the Schottky problem. So we'll get to the statement of the Schottky problem very quickly. And I wanted to overview various approaches to the problem. So everything here is only over the complex numbers. What happens over other fields is an exciting story that I will have precisely nothing to say about today. So mg will be moduli of complex curves of genus G. And Ag will be moduli of principally polarized abelian varieties of dimension G. When I speak from now on, I will always say just abelian variety, and I will always mean principally polarized. And I won't bother defining what the principal polarization is because I'm trying to give a survey, and that's not the direction I'd like to go. So there is a map that takes mg to ag. What it does, it sends a curve to its Jacobian. So the Jacobian of a curve C are the degree 0 bundles, so maybe degree G minus 1 line bundles on C, it's up to you. Or you can think of this as a quotient of a complex space of dimension G by a lattice. So geometrically, this is a complex torus, and the principal polarization is given by the theta function. So on a Jacobian of a complex curve, you naturally have a principal polarization given by a function on this complex torus, which makes this into an abelian variety. And this gives you a map that sends moduli of complex curves into the moduli space of principally polarized abelian varieties. And the Torelli theorem is a very simple statement. There's this arrow here, the injectivity of this arrow is the theorem of Torelli. And I don't want to go in that. So what the theorem says is if you know the Jacobian of a curve, you can reconstruct the curve from the Jacobian. Okay. And what is the Schottky problem? The question is, what is the image of mg and ag? And to tell you that there is something to do, let's compute dimensions. So by the way, this is supposed to be your introduction to history of the problem. So this is Carl Gustav Jakob Jacobi, who was born in Potsdam and died in Berlin. And of course, Jacobians are named after him. So let's think about the image of the moduli of curves in the moduli space of abelian varieties. So you can know maybe that the dimension of the moduli space of curves, this is a count due to Riemann, of course substantiated much later than that. So the dimension of the moduli space of curves is 3g minus 3. Well, in genus 1 it's special, it's 1. The dimension of the moduli space of abelian varieties you can also compute. So you maybe know that an abelian variety you can think of as being given by its period matrix, which is a G by G complex symmetric matrix with positive definite imaginary part. So what this means is the dimension of AG is equal to G times G plus 1 over 2. And as I said, dimension of MG is 3G minus 3. And these are complex dimensions. So you can see that in genus 2 and 3, the dimensions are the same. In genus 4, the dimension of the moduli space of curves is 9, while the dimension of moduli space of abelian varieties is 10. Then here it's easy to add 3, so I get 12 and 15, and here you get 15 and 21. And of course, in general, the dimension of the moduli space of abelian varieties grows quadratically with G. The dimension of the moduli space of curves grows linearly. So somehow fewer and fewer of abelian varieties in high genus are Jacobians of curves. And you see that perhaps the simplest, the first non-trivial case of the Schottky problem is here in genus 4. Because in genus 4, the dimension of the moduli space of curves is 9, while the dimension of the moduli space of abelian varieties is 10. So you expect that the moduli of Jacobians of genus 4 curves should be characterized within the locus of Jacobians, within the locus, sorry, of all abelian varieties with dimension 10 by one condition. And this condition was actually discovered by Schottky, which is why the whole problem is called the Schottky problem. We'll get to talk about this a bit later. Any questions so far? Okay, so that's the Schottky problem. So the Schottky problem is to characterize Jacobians among all principally polarized abelian varieties. And there have been many, many different approaches of various level of success developed to the Schottky problem over the years. One approach is due to Andreotti Meyer. There is Aldo Andreotti, who was an Italian mathematician, and here is Alan Meyer, who is a mathematician at Brandeis University near Boston. So what you do is the following. So you have an abelian variety A. So if you have an abelian variety, you should remember that it comes with a principal polarization. So A theta will be a principally polarized abelian variety. And what you can see, and that requires a proof, and this is not trivial. So for A generic, theta is smooth. So what is theta? So theta, recall, I will think of theta inside A is an Amble divisor with one section. So this is really the definition of principal polarization. Okay. So it only has one section, so I'm mentally identifying the divisor class with the actual subvariety, which is defined after translation. So you know that for a general abelian variety, the theta divisor is smooth. However, if I have the theta divisor on the Jacobian of a curve C is not smooth, and in fact, the dimension of the singular locus of the theta divisor of a Jacobian of a curve C is at least G minus 4. So this is a very special condition. This comes from so-called Riemann's theta singularity theorem. And the approach of Andreotti and Meyer to the Schottky problem is to try to characterize Jacobians of curves in terms of the theta divisor being singular. So the theorem here, this is the theorem of Andreotti Meyer, is the following. This is Andreotti Meyer, and this is 1960s. So let n G minus 4 inside AG be the locus of all principally polarized abelian varieties, such that the dimension of the singular locus of the theta divisor is at least G minus 4. Then the locus of Jacobians, so the image of the moduli space of curves, is an irreducible component of ng minus 4. So this doesn't quite solve the Schottky problem. It doesn't tell you precisely which abelian varieties are Jacobians of curves. This is what is known in the parlance in this field as a weak solution. So by a weak solution, what you mean is that you have some characterization of Jacobians up to extra components. So a weak solution to the Schottky problem is some kind of condition which will single out within the moduli space of abelian varieties some subvariety which is presumably reducible, may not be equidimensional, but such that one irreducible component will be the locus of curves. So the Andreotti-Meyer approach to the Schottky problem is an approach that gives you a weak solution to the Schottky problem that I just stated, that the locus of Jacobians of curves is an irreducible component of the locus of abelian varieties where the theta divisor is singular in dimension G minus 4. That was perhaps one first successful approach to the Schottky problem. The next theorem is a Matsusaka run criterion. Terahisa Matsusaka was a Japanese mathematician who worked in Brandeis, and Ziv Run works in University of California, Riverside. And their criterion is as follows. So theorem, That's the Matsusaka-Ron criterion. It's not a joint work, there are two separate papers with some different assumptions. I'm given a general statement. It says the following. So A theta is a Jacobian, so lies in the locus of Jacobians of curves, if and only if there exists a curve C in A such that if you look at its homology class, so the homology class of C is equal to what is known as the minimal homology class. So theta to the G minus 1 over G minus 1 factorial in H2 of A. Okay. So what do I mean by that? Theta is a divisor on a G-dimensional variety. So it's a class in H up to 2. Then you can take a G minus first power. This will be a sort of mentally an intersection of number of copies of the number of translates of the theta divisor. You can take this class, you can divide it by G minus 1 factorial, which is somehow its divisibility. So what you get here on the right is an integral homology class. And what the Matsusaka-Ron criterion says, if this minimal homology class is representable, meaning if there is a curve that has this homology class, then the abelian variety is a Jacobian. So in fact, in this case, what you see is that A is not just Jacobian of some curve, but it's a Jacobian of C. Okay. So this is a complete solution to the Schottky problem in the sense it's not a weak solution. There are no extra components. I'm cheating slightly. You should only take for most of this indecomposable abelian varieties which are not products. Let's not worry about that. So this is a strong solution, but it's somehow a cheating solution in the sense that if I were to actually give you an abelian variety and I were to ask you to please apply this criterion, you wouldn't know where to start because you would need to somehow construct a curve sitting inside this abelian variety. So the problem that's really solved by this criterion is the following problem. Given an abelian variety and given a curve sitting on this abelian variety, determine whether this abelian variety is a Jacobian of that curve. That's a somewhat weaker problem. You somehow have to start with a curve. But that's a very nice solution to the Schottky problem nonetheless. Okay, so let me now finally admit what is a theta function. So this is a formula here for the so-called theta functions with characteristics. So tau is a period matrix of an abelian variety. What I mean by this is the following, that the abelian variety A corresponding to such a period matrix is a quotient of C to the G by Z to the G plus tau Z to the G, right? And Z here is a point on this abelian variety A. And epsilon and delta are so-called characteristics, so they're elements in Z mod 2 to the G. And if you think about the locus theta 0, 0 of tau Z is 0 within this abelian variety, this is the theta divisor. So this is the equation of the theta divisor. So what did I just do? I just told you, without saying these words, that somehow I can think of abelian varieties as given by period matrices. So this really is a universal cover of the moduli space for abelian varieties by the Ziegler-Lappa half spaces metric G by G symmetric matrices that I have alluded to with positive definite imaginary part. And then I have written explicitly the formula for the theta function. So this is the function that defines the polarization divisor. You can ignore this formula if you want. What it does is it somehow says that this polarization can be defined over the modular space for abelian varieties up to this issue with characteristics of order 2. It shifts by 2. So what this corresponds to are shifts by 2 torsion points on an abelian variety. Okay. So why am I telling you about this is because I want to now tell you about a different set of approaches to the Schottky problem, which are more analytic in nature than this. So the approaches we had here were the Andreotti-Meyer approach, which told you something about the dimension of the singular locus of the theta divisor, and the Matsusaka-Ron criterion, which was something about homology classes of curves on your abelian variety. The approaches I want to go to now are somehow approaches that focus more on the theta function in a more analytic way. So let me try to go to that. Okay. So there is a Fay-Gunning Tri-Sequin, and this is what we're going to talk about now. So this is a photograph of Bob Gunning, who is a mathematician at Princeton, who I think some of you may have met. I couldn't find a single photograph of John Fay online, but he is a mathematician at Bowdoin College in Maine, who is very secretive about his life. Okay, so here are the so-called second-order theta functions. So given tau, which you think of as being an abelian variety, and given z, which you think of as being a point on an abelian variety, this expression here defines a function of tau and z. So this is something that somehow depends on an abelian variety and on a point on an abelian variety. And this is a collection of functions, because what these are indexed by, they again indexed by points in z mod 2 to the g. So there are 2 to the g of these guys. And each of them is a function on c to the g. So if I think of this as z being in c to the g, this is a function of z on c to the g. But if I think of this on an abelian variety A, which is c to the g quotient by z to the g plus tau z to the g, then each of these functions is a section of a bundle, of a line bundle on this abelian variety. And this bundle is the square of the principal polarization bundle theta. So I have just written for you 2 to the g functions. Trust me that they are functions, they are well defined. And the claim is, this is well known, this goes back to Jacobi, Riemann, and that area, H. And they were studied in particular a lot by Wirtinger, who I didn't put a picture of here. These are a basis of sections of 2 theta. And the Lefschetz theorem says that if I take the space of all sections of 2 theta, so if I take all sections of 2 theta, so if I take all theta functions of the second order, what they do is they take an abelian variety A, and they embed it in the projective space of dimension 2 to the g minus 1. Right? If I have a number of sections of the same line bundle, they give me a map to the corresponding projective space. Except this is not an embedding of A. These are all even functions. So they define an embedding of the quotient of an abelian variety by plus minus 1, which is known as the Kuma variety. So the image of this map is a so-called Kuma variety. I'll write it as cum of A. I didn't have enough space to put the picture of Mr. Kuma. So this is the Kuma variety, is a g-dimensional object in a 2 to the g minus 1 dimensional projective space, which is obtained by taking all the sections of 2 theta, which are given explicitly, if you wish, in this way. And the theorem, and these are a combination of a couple of papers of Fay and Gunning, is that this somehow gives you a solution of the Schottky problem. I will state the theorem a bit loosely. The statement is actually a bit weaker, I think, than what I'm writing. But this is roughly how you would want to think about it. So the statement is the following, that an abelian variety A theta is a Jacobian. And again, we should exclude the case of abelian varieties, which are products, if and only if the Kuma variety admits a family, admits a one-dimensional family of tri-sequent lines. Admits a family, it's actually of high dimension. So the dimension of the family is actually 4-dimensional, but for the characterization, it's enough to have a one-dimensional family. So let me explain what I just said. So what do I mean by a tri-sequent line? So you have a g-dimensional Kuma variety, which sits in a 2 to the g minus 1 dimensional projective space. So it's like a tiny object in a huge dimensional space. So you take 2 points of the Kuma variety, take any 2 points you like, draw a line through them. So you think you take 2 points, so this is 2g dimensions for 2 points on a Kuma variety, and you draw a line that adds 1 dimension. So somehow the set of points in the projective space that you expect to lie on such lines is of dimension 2g plus 1. The dimension of the projective space for g large is huge. So in general, expect that the Kuma variety will have no Tri-Sequin lines, that no line will intersect the Kuma variety in the projective space in 3 points for dimension reasons. You can also pleasantly check that if G is 2 or 3, you expect that you always have Tri-Sequin lines, which agrees with the fact that every abelian variety of dimension 2 or 3 is a Jacobian. Okay? So the statement of Fay and Gunning was a beautiful proof. There is also a beautiful proof by Welters from more pure algebra geometric approach, is that first of all, so the Tri-Sequin theorem, which is usually called Fay's Tri-Sequin formula, even though it was discovered by Gunning at the same time, and Gunning is very modest, is the statement that Kuma varieties of Jacobians have Tri-Sequin lines. And the paper of Gunning also contains a statement that if you have a suitable one-dimensional family of Tri-Sequin lines parameterized by a curve, then the Jacobian, then the abelian variety is a Jacobian of a curve. So this is again a solution to the Schottky problem, which says that an abelian variety is a Jacobian if and only if it has a family of Tri-Sequin lines. But again, it sort of requires you to start with a family, so you start with a curve worth of translates of Tri-Sequin lines, really. So again, it's a full solution to the Schottky problem, but you need to give yourself a curve within the abelian variety to start with. Okay. Any questions so far? The chat is empty, so maybe everybody is asleep.
Sam, sorry, just a small question. Before, you had that the abelian variety was just a Jacobian of the curve C in the previous slide.
Yes.
Now, is there a relation between A and this family? Like,
right. So somehow,
like that direct?
this is what I'm concealing here. So somehow, this family of Tri-Sequin lines, if you start with a Jacobian, the actual family of Tri-Sequin lines has dimension 4. And is parameterized by quadruples of points on the curve. So the precise statement is you should have a Tri-Sequin line such that you can translate this Tri-Sequin line, meaning you have 3 points where it intersects the Kuma, and you should be able to translate all these 3 points at once somehow.
Okay.
That's the precise statement of the criteria, and this is precisely what I really wanted to avoid here. But
okay, yeah, okay, sorry.
Yeah, so this is what I'm trying to conceal here. So there is a curve somewhere here, right? When I say a family, this means at least one parameter family. So there is some curve worth of Tri-Sequin lines, and I didn't want to say precisely what it was. Okay, so this is a very nice solution, very geometric. It's very beautiful. It relates to various interesting properties of theta dividers of Jacobians again. But again, it somehow is not really a completely nice solution to the Schottky problem in the sense it requires some extra data for family. It's not a finite amount of data. Again, it's something you wouldn't be able to check in any easy way. Okay, so the next, and this was proven in the 1970s. So this is 1970s. The next approach to the Schottky problem was a so-called Novikov conjecture. So this is Sergei Novikov. And this was proven by Takahiro Shota, and there are no photographs of Takahiro online either. So the conjecture is the following, and this was a theorem, a conjecture of Novikov that became a theorem of Shota. So this is the theorem of Shota in 1980s, where he proved the conjecture of Novikov, I think, from late 1970s, which says the following, that an abelian variety is a Jacobian of a curve if and only if it has a, I'll write something technical, then I'll explain what this has a 4-jet of a family of Tri-Sequin lines. Okay, so I don't want to go into full details of what this means, but let's think about what we just had. So we had a family of Tri-Sequin lines somehow parameterized. So this is a large family, meaning there is an actual curve worth of Tri-Sequin lines that you can find in Jacobian. Here it says that to detect Jacobians, you only need one Tri-Sequin line, and you need to somehow be able to perturb it to other Tri-Sequin lines with precision of order 4. So you somehow can expand this equation of a Tri-Sequin line to order 4 in the perturbation coordinates. That's what this says, and this is not how this was stated. This is equivalent to saying the theta function satisfies the KP equation. So the KP equation is the Kazantsev-Petveashvili equation, which is one of the famous equations in integrable systems. So the actual statement that was much easier to prove was that an abelian variety is a Jacobian if and only if the theta function satisfies the KP hierarchy, which is an infinite collection of commuting differential equations. Well, the conjecture of Novikov proven by Schroeder was that it's enough to satisfy just the first equation of this hierarchy. Okay. But I don't want to go into KP equations. I'm trying to follow the approach via sequence of the Kummer variety. And then this world, the statement here is that an abelian variety is a Jacobian if and only if it has a four-jet of a family of tri-sequence. There is some infinitesimal information about tri-sequence. This is somehow easier to check because it's a solution that's closer to a solution to the Schottky problem without giving you a curve, right? Because I only give you one tri-sequence, so one piece of data, and some kind of deformation. So the KP equation is some kind of partial differential equation satisfied by the theta function. It's not fully nice in a way because still it requires more data. And so the next statement was a Welter's conjecture. And this was proven by Igor Krichever. There is no photograph of Welter's again. So this is the theorem of Igor Krichever, proving the conjecture of Welter's. So Igor Krichever is a Russian mathematician at Columbia University. Welter's was a Spanish mathematician. So this was proven in 2010s, maybe 2009, 2008, I forget. Let's see, 2000s. Okay, which says the following, that an abelian variety is a Jacobian if and only if the Kummer variety has a tri-secant line. Okay, so somehow the Fay-Gunning theorem was that to detect Jacobians, you have to have a one parameter, really four parameter family of tri-secant lines. Novikov conjecture, Schroeder's theorem was that you only need a four-jet of a family tri-sequence. And the statement here is to say that to have a Jacobian, it's enough to have one tri-secant line. Okay? So an abelian variety is a Jacobian if and only if it has just one tri-secant line. So this is somehow a much stronger statement because you start with one tri-secant line, and if you somehow want to apply Fay-Gunning criterion, you somehow have to construct, starting from just one tri-secant line of the Kummer, a whole family of such things. And you don't even know how to deform. As Novikov conjecture, somehow have a four-jet of a deformation, which you want to extend to an infinite order jet and then argue some kind of integrability. So this is the strongest result in this approach to the Schottky problem. So this is the so-called Tri-Sequin Conjecture of Welter's, which was conjectured by Welter's in the 1980s, which was that the existence of just one tri-secant line characterizes Jacobians among all abelian varieties. Okay, so this is a great accomplishment. Let's now try to think whether that's something that's easy to check. So suppose I come and give you an abelian variety. So what does it mean I give you an abelian variety? Well, I'll just write for you a 5 by 5 matrix, say. And then I will ask you whether the Kummer variety has a tri-secant line. That's not so very easy to check, right? You somehow have to write this down. You have to look for these tri-secant lines. You can do it in principle, computationally you can. But this is a rather interesting geometric process, which is not straightforward. So what I want to do now is I want to finally get to the approach that Herschel, Farkas, Ricardo, Salvati, Mani, and I have been pursuing. So this is the original approach due to Schottky and Riemann. So let me be a bit more honest. So we have this collection of theta constants that I have, theta functions, which I'm now evaluating at z equal to 0, right? So these are functions of tau. And what they give me a map that takes some finite cover of moduli space for abelian varieties, and it embeds it in a projective space of some high dimension. Okay. And the Schottky problem is to try to ask what are the equations of the image of the moduli space of curves, right? So into here, you can embed, well, the suitable finite cover of the moduli space of genus G curves. So as a result, you'll see that you have a moduli space for abelian varieties is a subvariety in projective space. I have explicitly embedded it by so-called theta constants. And then inside that, I've embedded the Jacobians of curves. And you can ask, what are the equations that characterize Jacobians of curves among theta constants of Jacobians of curves among all abelian varieties? And the starting point for this investigation is not due to Schottky, it's really due to Riemann. So here is Riemann's so-called quartic addition theorem. Mr. Riemann. I actually never knew that his first name officially was Georg Riemann, because apparently he never used that. Okay. He died in Italy on vacation, but he was a German mathematician, again, quite some time ago. So this quartic addition theorem, if you look at it, what this is some kind of degree 4 polynomial equation among theta constants. So what this is an equation, this is a quartic equation, which is satisfied by the image of the moduli space for abelian varieties. So if you look at the moduli space for abelian varieties, it's embedded in the projective space by theta constants, and there is a whole collection of quartic equations. You don't have to understand what these are, so these coefficients here, there's all some numbers plus minus ones. So this is like plus minus 1, and this is plus minus 1, and whatnot. You don't want to go into that. Okay. So what this is to say that if you embed the moduli space for abelian varieties into a projective space, the image is again very small. The moduli space for abelian varieties has dimension g times g plus 1 over 2, so roughly g squared over 2. This is roughly 4 to the g. So you embed in a huge dimensional space because you have somehow, technically speaking, you have a line bundle which has too many sections. And then there are going to be tons and tons of equations satisfied by the image. And this is the quartic equations of Riemann. The conjecture is that these are all the equations. That's not known. Okay. But I want you to keep in mind that that theta constants of general abelian varieties satisfy some quartic equations of this form, which were discovered by Riemann. Okay. So this is not about the Schottky problem. The Schottky problem is named after Friedrich Hermann Schottky, who was a mathematician also in Berlin. And what Schottky did is the following. Theorem, Schottky, so this is 1880s, which says the following. If I take an abelian variety of dimension 4, he is a Jacobian of a curve if and only if its theta constants satisfy some equation p of theta epsilon delta is 0. And Schottky has written down this polynomial in theta constants. So the statement of Schottky is that this is a complete solution to the Schottky problem in genus 4. So you may recall that in genus 4, the dimension of the moduli space of curves of genus 4 is 9. The dimension of the moduli space of abelian varieties of dimension 4 is 10. So we have one condition, and Schottky has written down this one condition. So let me try to elaborate a little more on this. So what do we have? We have the Jacobians of curves, right, which sit inside the moduli space of abelian varieties, which itself sits inside projective space of some huge dimension embedded by theta constants. So in genus 4, this dimension is 10, this dimension is 9, this dimension is huge. And this is roughly 500 or whatnot. It's unbelievably huge. And what Schottky has written is he has written one equation which characterizes the Jacobians of curves among all abelian varieties. It doesn't mean that he has characterized the image here. He has only characterized the image of Jacobians of curves within the model of abelian varieties. So what this says is, if you now want to solve the Schottky problem explicitly in genus 4, if somebody comes and gives you a 4x4 matrix symmetric with positive definite imaginary parts with complex entries, and you want to check whether this 4x4 matrix is a Jacobian of a curve, all you need to do is you need to compute the theta constants corresponding to this matrix, plug them into the Schottky polynomial, and check whether the Schottky polynomial vanishes. So this is somehow a very explicit solution to the Schottky problem that is due to Schottky. Okay. Any questions so far? Seems no. Okay. So in this sense, the Schottky problem in genus 4 is completely solved. And the situation is that in any higher genus, there is no such complete solution. So I'd like to now tell you what the Shortcase equation is, where it comes from, and how it arose. I won't go through the full details, but I want to tell you that it comes from so-called prim varieties. So you start, so this is Friedrich Prim, who has a very interesting story. So again, this was quite a while ago. So the Prim manufacturers is one of the largest still existing German manufacturers of haberdashery, of various items of clothing and so on. And Friedrich Prim was a mathematician who was also a member of this very rich and very wealthy industrial family. Consider an unramified double cover of curves. We take C twiddle is a double cover of a curve C. Suppose your curve C has genus G, so it lies in MG. Then you can check from Riemann-Hurwitz, if you wish, that the covering curve will have genus 2G minus 1. If you have such a double cover of curves, I can look at the Jacobian of C, twiddle, and this will map to the Jacobian of C. Let's call this map pi for prim and for projection. And then you can look at the kernel of pi, which is a subset of the Jacobian of the covering curve. And you can look at the connected component of the identity of this. So what this is this is going to be an abelian variety of dimension G minus 1. Because the Jacobian of C is a G-dimensional abelian variety, the Jacobian of C twiddle is a 2G minus 1 dimensional abelian variety. So the kernel is a G minus 1 dimensional abelian variety. This is an abelian subvariety of the Jacobian, so it's naturally polarized by the polarization of the Jacobian. The miraculous statement, which was rediscovered by Mumford, who proved it algebra geometrically, was that this variety is called the prim variety. So prim variety of this double cover is this kernel. And it turns out to be principally polarized. Okay. So somehow what this means is that if I start with a cover C to C like that, there is a way to construct from it a prim, which is an element of a G minus 1, which is a G minus 1 dimensional principally polarized abelian variety. Okay. This construction is due to Prim. And he has considered this principally polarized abelian varieties, and he has considered their theta functions, but not in the language we are currently using to talk about algebraic geometry, but this was a construction of Prim varieties. Okay. And now let me tell you how this construction relates to the Schottky problem. So I'll tell you about the so-called Schottky-Jung proportionalities. And they were discovered by Schottky and Jung, who was a student of Schottky in 1880s and 1900s, but they were actually proven by Herschel Farkas, whose photograph you've seen on the first page with my colleagues on this, and by Harry Rauch, who was a mathematician at CUNY at the City University of New York. And this, what they do is they relate the theta functions, theta on the Jacobian of this double cover, on the Jacobian of C, and on the prim variety of the cover. Okay. And let me first say what data you need. So if you have a prim variety of the cover, so given a cover, giving a cover, an unramified double cover is determined by a point, which tells you what this point is, by a point usually denoted eta, which is a point on the Jacobian of C of order 2. So somehow, if you want to consider, if you want to enumerate all unramified et al., if you wish to call them that, double covers of a genus G curve, they're all indexed by 2 torsion points in the Jacobian. So somehow, given a 2 torsion points in the Jacobian, you think of this as a prescription how to glue the double cover. So how do you do a double cover? So here is my curve C, and I want to take a double cover of it. So I'll take 2 copies of C, put them one above the other. That's a trivial double cover. That's not very exciting. But if I have 2 copies of the curve C, what I can do is I can take scissors, take some cycle on the curve C, cut both copies of C along the cycle, and glue the boundaries crisscross. And this will give me now a connected double cover. And then what I have to tell you which double cover I'm going to take is which cycles I'm going to glue this way. And that's precisely the data of a 2 torsion point in the Jacobian. Okay? So the Schottky proportionality is this. So it's a relation that relates theta constants of the prim, this is a prim, and theta constants of the Jacobian that you're covering. And this is for a specific choice. This is written here for a specific choice of a 2 torsion point, which in this coordinates is this one. But never mind that. Okay. So what does this Schottky proportionality do? What it does, it relates the theta constants of the prim and the theta constants of the Jacobian. So why is that interesting? Why is that useful to try to get a solution of the Schottky problem in genus 4? Well, what you can do is the following. So you take this Riemann quartic identity. So this is a quartic relation satisfied by theta constants of any abelian variety. In particular, they're satisfied by theta constants of a prim. So your prim variety is a G minus 1 dimensional principally polarized abelian variety. Each theta constant satisfies some degree 4 equation written here, which let's not forget. And let's go here. So if we look here, what we're seeing is the following. So in this Schottky proportionality, on this side, what I have are theta constants of the prim. And as I just said, they satisfy a degree 4 equation. So there's some kind of polynomial of this stuff, which is 0. That's the Riemann quartic identity. But if I take this polynomial and I just substitute this identity into it, what I get is I get a way. So if I have a polynomial on theta constants, theta constants of the prim, is then equal to some other polynomial, and there is some issue here, some technical issues I'll probably get to in 5 minutes, is basically equal to some polynomial in theta constants of the Jacobian. So this means, for example, if I have any polynomial of theta constants of the prim that vanishes, this gives me a vanishing polynomial in theta constants of the Jacobian. All I know about prims at the moment is that they are abelian varieties. So this means that if I take any abelian variety and I take any equation satisfied by theta constants of any abelian variety, this will be satisfied by theta constants of the prim, which means I will then get an equation satisfied by theta constants of the Jacobian. And this is precisely what Schottky has done. So Schottky's solution to the Schottky problem in genus 4 takes the Riemann quartic identity, applies the Schottky proportionality above, and gives an equation in genus 4 that will be satisfied precisely by theta constant of Jacobians and nothing else. Notice one issue, that the Riemann quartic identities are of degree 4. The equation that Schottky gets are actually of degree 16. And the reason is this square here, because if I start with an equation in theta constants of the prim, I only know that theta squared is some polynomial in the theta constants of the Jacobian. So there is some need to normalize this, to somehow regularize this. Keep this in mind for 5 minutes from now. Okay, but again, Schottky's approach is as follows. Okay, so what this means is that the way Schottky has obtained the solution is he's taken the Riemann quartic identity satisfied by theta constants of any three-dimensional abelian variety. Then they're satisfied by a prime of any genus 4 curve. And then he gets a polynomial satisfied by theta constants of a genus 4 Jacobian. And this is a Schottky solution to the Schottky problem in genus 4. Okay, there is a Agusa solution to the Schottky problem. This is Junichi Agusa, who is a Japanese mathematician who worked in Johns Hopkins University. And his solution is so nice I can write it down. Schottky's equation I don't want to write down because the combinatorics is very unpleasant. The combinatorics of our solution is no better, but it's ours, so we'll write it down. But here, this theorem of Agusa is the following that says if I have a 4-dimensional abelian variety, it's a Jacobian of a curve if and only if the following identity holds. If 2 to the 4 sum of 16 powers of theta constants is equal to the sum of 8 powers of theta constants quantity squared. 16 should be written. So that I take the sum of all 16 powers of all theta constants. The sum here goes over all characteristics epsilon delta in 0, 2. So this is the degree 16 equation on theta constant. So what this says is that if you want to now check whether a genus 4 abelian variety is a Jacobian, there is a very nice, very symmetric looking polynomial in theta constants that you need to evaluate and check whether it's 0, whether the two sides are equal. So this is Agusa's reformulation of the solution to the Schottky problem in genus 4. The way you obtain this is very nice, but goes beyond what we do. Unfortunately, in higher genus, no solutions, no known solutions, no such nice equations, no known for any higher genus. So despite the fact that Schottky has solved the Schottky problem completely in genus 4 140 years ago, somehow there is still no complete solution in this classical sense for higher genus. And this is what we have done. So here is our result. So here is a theorem. Maybe looks a bit overwhelming. Okay, so here is a formula. So let's call this gadget S3, 4. Okay, and let for any other indices, excuse me, Sj, Sij be the same, but with columns 3, 4 swapped with columns ij. So I get a bunch of equations, S3, 4, S3, 5, S3G, so on and so forth, up to Sg minus 1, G. So the total number of equations you can compute as G minus 2 times G minus 3 over 2. Then the claim is that the Jacobian locus is an irreducible component of the common zero locus of all this. Okay, so what am I saying? I'm saying that this is an explicit solution to the weak Schottky problem. Again, so what I'm saying is here is a bunch of equations. We'll look at them together in a second. So there's some explicit polynomials in terms of theta constants of some huge degree, unfortunately, but that's life, right? Because there's some huge product, its degree is very large. And I have written down for you one equation, and the rest are obtained by permuting the columns in this expression. So I've written down a number of polynomials of theta constants in theta constants. And the claim is that if all of these polynomials in theta constants vanish, I'll respond to the question in chat in a second. If all of these polynomials in theta constants vanish, then get some locus in the Euler space for abelian varieties. And the claim is that the locus of Jacobians is an irreducible component of the locus of common zeros of all these polynomials and theta constants. So this is a completely explicit solution in the spirit of Schottky, Riemann, and all that to a weak Schottky problem. We do not claim, and it is not true, that our collection of equations are characterized precisely as the Jacobian locus. There are going to be extra components. The reason I computed the total number of equations is because I want to say that this number of equations is precisely equal to the codimension of the locus of curves within the locus of abelian varieties. What this means is that this is somehow local, that the locus of curves is a local complete intersection. We have just written local defining equations near every point of the locus of Jacobians of curves. So that's the statement. Now let me spend half a minute on what this is. So what are the features of this wonderful formula, which maybe you don't think is wonderful, but let me try to convince you it is. It's not so bad. So there is this horrible product here, right? Over all choices of tons of signs, there are lots of choices of those. So this is going to be a very high degree thing. Then there is a sum. The sum goes over all genus G minus 4 characteristics, right? So this epsilon is a collection of zeros and ones of length G minus 4. If you now look at this characteristic here, so this epsilon at the end has genus length G minus 4, and then I am prescribing what happens in the first 4 columns. And then I'm prescribing this again and again and again. And then there is this E, which appears everywhere. And this is here to ensure that all characteristics are even, because actually there are even and odd theta characteristics. And the theta constants with odd characteristics vanish identically, so we don't want to see them. So what you see here is a completely explicit equation. And if you think about genus 4, so in genus 4, this is not there is no sum. And what you get in genus 4 is precisely the Schottky's 1 equation, nothing else. Okay? So this is some kind of generalization of Schottky's equations to arbitrary genus. Okay, let me now answer the question in the chat. So the question in the chat was, in Agusa's theorem, so I'll go back, there are several 4s. What makes that an analogous formula that does not work for other genus other than 4? I'm very glad that somebody asked that. Thank you. So there is one 4 that you see here, right? This is this 4. I don't see any other 4s. So the 16 and 8 are there because somehow theta constants are modular forms of weight 1/2, and there are various transformation properties that make you start writing equations if you want them to be so nice, only with 8's power. So this 8 and 16 should really be 8 and 16. But it's very tempting to think that this 4, which I have written so badly, I've written so badly because this should be a G, right? It's very tempting to think that what I've just written with a G here should be an equation that is satisfied by Jacobians of curves for any genus G, starting with genus 5. This was conjectured by many people, including Knizhnik, Belavin, Fong, Docker, and a bunch of other people, motivated by physics and superstring scattering amplitudes. And Ricardo and I, about 10 years ago, have proven that if you write 5 here, and you look at genus 5, this equation is not satisfied by Jacobians of genus 5 curves. Yes, I know that 16 is 2 to the 4, but that's, it's a coincidence. So somehow if you look at the equation, so the Schottky original equation, so you take the Riemann quartic, which is degree 4, but then there is a square root, so you somehow need to choose different signs. So you'll have to take a product of 4 different expressions with different choices of signs. So the 16 is really 4 times 4, and the 4 is the Riemann quartic 4, and the other 4 is 2 to the 2. So that does not generalize so easily. So somehow, I know that 16 is, of course, 2 to the 4, but the reason that 16 arises here is not that. So there is no known generalization of this statement. Okay, so that's a very nice result, but if you try to generalize this again by writing 2 to the g here, this modular form will not vanish for any genus starting from 5, even though it was conjectured to vanish. Okay, I hope I answered the question in the chat. Okay, so let's go back to our solution here. So the solution here is, we have written down a collection of modular forms which vanish on the locus of Jacobians of curves, and such that their common zero locus contains the locus of Jacobians of curves as an irreducible component. So, as I hoped, I have run out of time before I get a chance to talk much about the proof, but let me try to ask you the following question. Why didn't Jacobi, and Riemann, and Schottky, and Prim, who were all very smart people, and who knew very well how to manipulate with theta functions and theta constants, why did not they come up with that? Because if you look at this, this is a statement that you can imagine seen in a paper of Schottky. There is nothing here, and they didn't worry about local reducible components at that time so much, so they just say define locus of Jacobians. But apart from that, this is some kind of a statement that is very, very classical. So why didn't it show up 100 years ago? So let me spend a couple of minutes saying what we do. So the method of proof that we have is something that's also goes back far in history, but somehow has not been fleshed out and hasn't been as clear in people's minds as it is now. So the idea is expand the equations near diagonal period matrices. So basically what you are imagining is here is your picture of a genus 3 Riemann surface. And you imagine that you are pinching this Riemann surface by shrinking this loop here and this loop here. So you're somehow pinching. So it becomes basically 3 elliptic curves. So you see that when you pinch fully, the Jacobian will be just the product of the Jacobians of 3 elliptic curves. So your period matrix will have this form. It will be diagonal. And then you can ask, maybe I'll write that, let's denote T1, T2, T3, the entries on the diagonal, and then will be a 0 here and 0 here in the limit. But then as you're pinching, you're somehow approaching this. So you can look at the equations we've written down, and you can write down their expansions near the diagonal. And this is a Taylor expansion. This is just a Taylor expansion of a theta function near the diagonal. So that's the expansion. So using that, again, I haven't told you anything that the ancients, meaning Riemann, Schottky, and Prim, didn't know. They knew how to do that. The reason they knew that, they knew even more. So this is Poincaré, whose first name was actually Jules and not Henri, as we all were led to believe. Okay. So here is a so-called Poincaré infinitesimal relation. So he asked himself the following question. In genus 4, which was the only situation which was solved, near the diagonal, so in genus 4, you have a 10-dimensional modular space for abelian varieties, and within that you have a 9-dimensional locus of Jacobians. And you know that the locus of Jacobians somehow approaches locus of diagonal period matrices, because you can just take this, what I've just drawn, but in genus 4, so 4 elliptic curves, 4 genus 1 curves put together. So then the period matrix will be purely diagonal. And then Poincaré asked, what are the equations, what is one equation that defines the Jacobian locus near the diagonal? And that's the one equation he has written down. So this is the entries of the period matrix. And it's very nice, and it has three terms. Okay. And this, in fact, generalizes to arbitrary genus. So in fact, an arbitrary genus, infinitesimally, such equations hold. This was not written by Poincaré, wasn't necessarily clearly believed by Poincaré, was believed by Rauch, and there is a proof by Rauch. We gave a different proof. So let me say what the method of proof is. So we have our equation here. We expand it near the diagonal. And what we'll get is, we claim that what we get is such equations of Poincare type times some polynomials and theta constants of the diagonal period matrices, which are non-zero. And then if you look at these equations of Poincare type, you can just eliminate variables one by one. So what we see is that locally near diagonal period matrices, our equations cut out a locus of dimension 3g minus 3. The way we get our equations is by applying Schottky proportionalities to Riemann quartic identities. So we know that our equations are satisfied on mg. So this locus is going to contain the Jacobians of curves. But then this is also dimension 3g minus 3. So this means that the equations cut out near the diagonal precisely the locus of Jacobians of curves, and every other component is elsewhere. So this is how we prove it. If you think about it again, this is something that Poincare and Schottky could have done. So there was a slide here that I could have spent talking about the difficulties. It's luckily empty. So let me say in words what the difficulties were. So the difficulties is if you try to apply the Schottky proportionalities in the most standard form, so if you look at them, they're very nice, but they are for one specific choice of a two torsion point, which is this choice of a two torsion point. If you somehow try to do Schottky proportionalities with this two torsion point, what I just said will never work. Somehow, if you just work near the diagonal, you will always get cancellation. You will just get zero. You won't see anything. You will need to expand to higher order and you won't see anything. Furthermore, as I said before, when you're applying Schottky proportionalities, there is a square here. So if you try to apply, you'll have to multiply pieces with different signs, plus or minus. And again, you will not be able to control anything and you might get a cancellation. So somehow, even though we don't use a computer for the problem at the end of the day, somehow some of the motivation came from playing around with theta constants. And by playing around with theta constants and with two torsion points, we were finally able to find a collection of Riemann identities such that applying Schottky proportionalities to them with the correct two torsion points will give you a collection of polynomials and theta constants, such that if you restrict them near the diagonal, somehow you can figure out the lowest order term of the expansion. Basically, you'll have tons of terms. You remember our equation had the product of a huge number of things, each of them which was a sum of a huge number of terms, but somehow there will always be a lowest order term. So this means you will somehow at the end of the day know what the lowest order term of the expansion is. And this means at the end of the day, you will be able to see that the lowest order terms will just give you Poincare relations, and then you will just eliminate from them variables one by one. So somehow T34 from here, tau 34 will be expressible in terms of the rest and so on. So you can see immediately that the locus you get is 3g minus 3 dimensional. As a byproduct, we reprove Poincare relations in full generality, which Poincare did not prove. So that's what we do, and this is an explicit weak solution to the Schottky problem, and that's all I wanted to say. And hopefully next time I'll be back in Pucon. Thank you.
Thank you so much. So please, thanks, Roman.
Bravo. Bravo.
So I think you answered the question was in the chat, and there is another questions around in the chat. I don't see it.
No,
In the chat, no, I don't think so.
The chat is no. So if anyone has a question, please unmute yourself and ask.
I have a question.
Yes.
I have two questions actually. One, have you been able to identify any of the other components in this locus geometrically?
No. So we don't know the geometry of the other components of this locus. And we have written down the number of equations equal to the codimension. You can play around with the combinatorics a bit more. You can write more equations. But even in genus 5, if you write more equations by permuting, by acting on this, by suitable transformations, by permuting, you will still have extra components. And we have no idea what these extra components look like. So we don't know what the dimension is. We don't know anything about them. So in genus 4, there are no extra components because we get the Schottky equation and we're done. Already in genus 5, we have no idea. We have almost no idea.
Okay. And my other question has to do with the Tri-Sequin conjecture. In the case of when you have a degenerate Tri-Sequin, it seems like you can construct a curve because you have some kind of information about the direction that the Tri-Sequins go. Is that
So a degenerate Tri-Sequin is a case of a so-called flex point, right? So you have a line which intersects the Kuma variety with multiplicity 3. So you have a vector. So you somehow know your curve should be tangent to your vector.
exactly?
So that's the amount of data you have. But that's only vector in one point. So you have no idea. I mean, the curve is going to bend, right? It's not going to be linear in the Jacobian.
Mm-hmm. But for me, the surprising thing is in the bona fide Tri-Sequin case, it seems it's surprising to be able to obtain an actual curve just from one Tri-Sequin. It doesn't seem like there's a direction where you can go. Is there any geometric idea behind that, or?
There is no proof. So there is recently a paper by Arborello, Codoni, and Foresti, which appeared recently online, which proves algebra geometrically. I cannot tell you the full details. I haven't understood them yet. The Tri-Sequin conjecture for the fully degenerate case of a flex line and the half degenerate case, which is when you have a Kuma variety and you have a line that's tangent at one point and intersects at another point. So these are sort of not fully discrete cases. Somehow they still don't get the fully discrete case of an honest Tri-Sequin. I mean, I understand how Igor Fischer's proof goes because we have done some other work on prime varieties using similar methods, but somehow it doesn't tell you geometrically why it works. So basically, the proof proceeds by checking that you can construct an integrable hierarchy satisfied by the theta function, and the machine works.
Okay, thank you.
Well, Samuel, I want to ask a question similar to Robert's first question is, you say, okay, in your equation, you have these polynomials and you have one irreducible component which corresponds to Jacobians. And so this irreducible component intersect other irreducible component. These intersection points correspond to very nice Riemann surface. Can you say something about them?
Not much. So we don't, so the issue is, I don't know what other components it intersects. So somehow our proof works at a generic point of the diagonal period matrices. And I can try to look for period matrices which are diagonal where this component will intersect other components. And I can tell you this doesn't happen. So somehow locally near the diagonal, there are no other components essentially. I mean, except if you go into, never mind. So all the other components will be sort of locally reducible. But it could be that I have, that's the main difficulty to my mind in going from a weak solution to a Schottky problem to an actual solution. So suppose I write down some really nice equations, and they're not going to be, the number of equations is not going to be equal to the codimension of the Jacobian locus, presumably. It will be much higher. So if I write, a gazillion equations and I swear to you that they classify, that they characterize just the Jacobians of curves, it could be that I'm missing some point somewhere, just one isolated point. And there are just no techniques to work with this. So what could happen, and what I believe happens, is there are many other irreducible components that could well be just disjoint from the Jacobian locus that don't intersect it. And this I have no idea how to control. I know you didn't ask that. That's the question I wanted to answer. So in regard to the question you asked, I don't know how to detect the points where this intersects something else. So along the diagonal, I have local manipulations, I can do that. But these are a collection of rather annoying and complicated equations. So if I had some point where two components intersect, this means it's a point of non-smoothness of the common zero locus of these equations. But if I imagine just writing down the Jacobians, the Jacobian is a matrix of the Jacobian determinant, the partial derivative with respect to tau, that's an unbelievable mess unless I'm at the diagonal. So I don't know how to detect anything else.
Thank you. So any more questions?
Oh, just, this is Ricardo, hi.
Yeah.
So just let's say something about the 16 case. So just, Sam, you know that there are some equations of degree 16 and that they've been found by Bert van Gemmen. And these are really obscure. did you have some feeling about this equation or no?
Precisely zero. So what Ricardo is referring to is somehow a subject I haven't really gone into. So the equations we write are of some unbelievably high degree, basically 2 to the g. I mean, they grow like 2 to the g. I don't forget the constants. But you can ask whether there are any equations satisfied by the Schottky, by the locus of Jacobians in genus G, which are of fixed degree independent of G. And there are some equations that have been written by Bert von Hemmen, and I don't know how they fit into this picture, but they are very interesting. So I also didn't mention, but somehow this approach to the Schottky problem via the Schottky proportionalities has been consistently studied very carefully by Bert von Hemmen and Ron Donaghy in 1980s, who proved that this approach in principle gives a weak solution to the Schottky problem, but it's in principle because somehow the approach needs all equations among theta constants of general abelian varieties in genus G-1, which is of course not available. Sorry, thanks for reminding me to say that. I don't know, Ricardo, I have no idea how to think about Bert's equation.
Well, I hope that meanwhile you got some idea, but
No, hasn't changed.
okay.
So any more questions around? No? So if not more questions, then we thanks again Samuel for his beautiful talk.
Thank you.
Thank you, Samuel.
Thank you, and I hope we'll meet in person someday.
Yeah, of course, we're waiting for you here. So I think this was the last part of our session today. I don't know if we have another video.